Let's now introduce the subnormal numbers. Now what we've seen in the previous video was a normal number times a normal number giving a normal number. But as soon as we introduce another type of number, which we call our subnormal numbers, then we're not going to just have one output, we're going to have 4 different outputs here. So we could have the possibility of having a normal times a normal giving a normal, which was the first one we've already looked at, and we could have a normal times normal giving a subnormal. We can have a normal times a subnormal giving a normal, and a normal times a subnormal giving a subnormal. Now we could also have a subnormal times a subnormal, but that's going to head off towards 0, so it's going to underflow to 0, so we're not going to bother looking at that one. But each of these has a possibility of behaving differently. So that means that before we can get started on looking at how we work with subnormal numbers, it's a good thing to be able to test for the subnormal numbers. That is, we want to be able to test whether we've got a normal times a normal coming in, and we want to test whether we've got a normal times a subnormal coming in, and we want to be able to test whether the output is going to be normal or subnormal. So let's look at the test first of all to find out what type of number we're getting coming into our system here. So we want to test for normal and subnormal inputs. Now the difference between normal numbers and subnormal numbers are that the exponent for a subnormal number is all zeros. So the exponent bits, the 8 bits, are all zeros. But for a normal number, we're going to have one of the values of those 8 bits is going to be a value of 1. So in order to test and find out whether we've got a normal number or not, we can use an OR gate. So we can OR all of the bits together. So whenever we've ORed all of the bits together, if we get at least one value, which is a high, then we'll get a high output. So I've just put the OR, the truth table there as a reminder. So what we can do is, in order to test whether we've got a normal and a normal coming in, we can OR the value of EX, so that's the exponent for X, and we can OR the value for the exponent for Y. So if this is high and this is high, that means that both of these must be normal numbers. So this is a test to ensure that we've got a normal times a normal. So that's 2 of these dealt with. Now we're looking to find out how we do normal times a subnormal. So again, if we were to OR the exponents for the X value and OR the exponents for the Y value, it's going to tell us whether we're going to have a normal or a subnormal for each of them. And then what we can do in this instance here is we can, rather than AND them, we can exclusive OR, because in this instance here then what we have to have is at least one of these is going to have to be true. So either this one here is true, or this one here is true. But we can't have both of them be true. If both of them were true, then we wouldn't have a normal times a subnormal. If both of them were false, we wouldn't have a normal times a subnormal. So we have to be sitting using an exclusive OR in order to test these. So what we can do then is we can write out this little truth table here, or we could build a circuit just using these simple gates. So we can OR the exponential for X, we can OR the exponential for Y and exclusive OR them, and that will tell us whether we're going to have a normal times a subnormal input. So now we have to look at the outputs and find out how we can tell whether our output is going to be a normal or a subnormal. So let's look at that next. Now we want to check and find out whether the output is a normal number or a subnormal number. Now we know that for a normal number, the exponent range is between plus 127 and minus 126. So that means that if we were to add up the exponent for EX and exponent for Y, then it would still have to be within that range of minus 126 to plus 127. So here's a test to find out whether the number is a normal number. It's got to be greater than equal to minus 126 and less than equal to 127. Now we could do the same for the subnormal numbers. We know that the subnormal numbers are going to range between minus 126 and minus 149. And we could do the same for the overflows. So it's going to overflow if it's a number greater than 128. And it's going to underflow if it's a number less than minus 149. Now that is not the end of the matter. It might seem a reasonably simple and elegant solution, but it doesn't actually work out just as simple as what we have here. Now we're going to run into three problems if we try to solve this using the simple scheme from the previous slide. Now the first thing is that the subnormal numbers have an unbiased exponent which is a fixed value, which is minus 126. So it doesn't matter what subnormal number we have, how large it is or how small it is, the exponent remains fixed at minus 126. So if we don't have any varying exponent, then we can't use the method we've seen in the previous page for the normal numbers, that is simply adding up the exponent values. Now secondly, whenever we multiply some normal numbers with subnormal numbers, the summation of these two values actually lies within the normal range. So although you're getting a subnormal answer, if you were to simply add these things up, then it would be telling you that in some instances you're actually getting a normal answer. So again, that just wouldn't work. Now there's a third thing which regards the actual implementation of a floating point unit, and that is that the exponent value that we've seen for a subnormal number, it ranges between the minus 127 to minus 149. But if we have an 8-bit exponent, we can't represent numbers less than minus 128 with our 8 bits. We would have to add on an extra bit in order to represent numbers that are of a value minus 128 to minus 149. So we have a solution to these problems, and it's something that makes our lives a whole lot easier. So what we want to do first of all is we want to take any subnormal inputs and we want to make them into normalized numbers, and I'll show you how that's done in the next video. Now secondly, once we've done that, we need to extend the range of the exponent from 8 bits to 9 bits. Now I've written here internally extend it because in effect this will become like a hidden 9th bit of the exponent, in the same way we've got a hidden 24th bit of the significand or the mantissa. Now the third thing we have to note here is that the subnormal exponent is no longer going to be the value, the fixed value of minus 126. It's going to vary, and it's going to vary from minus 126 to our value minus 149. So that variation is going to be given by this LZC. So this LZC, it's the leading zero counts. So what we do is if we count the number of leading zeros in the subnormal number, then this will give us the new subnormal exponent value. Now it might not seem obvious when I just talk my way through this here, but what we'll do is we'll go on in the next video and we'll go into the tool and I'll show you the difference that occurs from whenever we normalise these results. So just before we finish this video, I'd like to say that I actually spent a couple of weeks on this section. Whenever I first put together the algorithm in Excel VBA for the multiplication, I never normalised the subnormal numbers, and you can get it correct without normalising the subnormal numbers, but the solution just isn't as elegant. It's not as elegant in the code, and also you'll see in the future it's just not as elegant when we come to realise it as a floating point unit. And this normalising the subnormal numbers and extending the exponent range by an extra bit tends to be the preferred option, and that's the option we're going to continue with in the rest of the videos on the multiplication. So thank you for listening. I'll get you in the next video. Goodbye.